Hello everyone, welcome to the notes for Guided Notes 3.2, Light and Waves. In these notes we will look at the guiding question, how can we use the light emitted by elements in a flame test to identify the energy of the light and the identity of an unknown element. So for notes, you're going to need a highlighter this time. So to understand quantum theory, we must know something about the nature of waves. A wave is a vibrating disturbance that transmits energy. The electromagnetic spectrum is a type of wave. Waves are made up from packets of light energy called photons. This is the electromagnetic spectrum, where it shows you the relationship between the type of wave here, the length of the wave or wavelength here, and the frequency or how many waves per second, which is what Hertz is, how many waves per second occur at each type of wave. Okay, so the length and speed of a wave determines where on the electromagnetic spectrum it falls. We have three equations that we will look at. In class on my whiteboard, I have posted the stuff that you need to write down on the back of your periodic table. It includes these three equations and these variables with what they are, and either their units or the constant value. And we wrote this very small in the top left corner on the back of our periodic table, so that way we can use it as a reference on the test. The visible light spectrum is part of the electromagnetic spectrum. This part is the part that our eyes can detect. Red light has a wavelength of 700 nanometers, which is over here, and violet light has a wavelength of 400 nanometers, and that is the generally accepted range of visible light on the electromagnetic spectrum. So we have a quick example in the middle of our notes. You will need a calculator for this part. So the question asks, what is the energy of green light? Well, using the previous slide where we saw green light, we would see that the wavelength of green light is about 525 nanometers, and we have energy. Okay, so looking at the three equations that we talked about just a couple of minutes ago, we would look and see which equation has energy and wavelength, or lambda, in it. And we would see that it would be the equation E equals hc over lambda. It is asking us for energy, and the equation has already been arranged so that energy is by itself, so we do not need to rearrange it. The other thing we need to pay attention to is that all of the units are not derived, so we have to get rid of the nano. We wrote down, or were told, that nano means times 10 to the negative 9. This is nano, and so we can substitute it in and then add meters at the end. So we have 525 nanometers here, and 525 times 10 to the negative 9 meters. These are equal. Remember, if you were to write this as an answer, you need to put it into the correct scientific notation format, so you move the decimal place twice, so the exponent increases by 2, and this is still meters. You can use this one, though, in your math and calculations. I will not dock using that one. So now we're ready to substitute in. We know h because it is a constant. It is Planck's constant, and that is 6.626 times 10 to the negative 34 joule seconds. And this is a constant, so the units sometimes are weird to allow all the math to work out so you get the right units in the end. It's experimentally determined and accepted at that with the units given. So, speed of light is 3.00 times 10 to the 8th meters per second because it's a speed. And then wavelength was given to us, and we rewrote it in terms of meters. So the meters cancel, seconds on top, and dividing by seconds, those cancel. And so we're left with just joules, which is what we know the unit for energy is. Doing the math, you would plug in 6.626 and then find the E button. It usually looks like this, or if you have a graphing Texas Instrument calculator, you'll see a comma and the EE will be in blue. You'll have to hit the second button and then that comma. So anytime we have an exponent, that E means times 10 to the whatever power. So 626E, and then don't make it a power, just write it down or type it in. So E negative 34, make sure it's a negative, times 3E, you don't have to include the zeros unless there's another non-zero digit, 8. And then you'll hit the enter or equal button, and then you will divide, and then 525E negative 9, and then hit the equal button again. So this is what you would type into your calculator. And when you do that, you should get, and you should practice and check, 3.79 times 10 to the negative 19 joules. Okay, so let's look at the history a little bit more. Max Planck was a German physicist in the 1900s. He analyzed data from the radiation emitted by heated substances at various temperatures when a light bulb filament glows. He realized that atoms and molecules only emitted energies in certain quantities, and he called them quanta. Quantum is just another word that means a small amount, and in this case it means a small amount of energy that is either absorbed or emitted in the form of electromagnetic radiation. The energy of this electromagnetic radiation, he saw, was always in integer multiples of h times v, which we said that in our equations is equal to energy because he discovered it. When he presented his theory, he could not explain why this occurred. However, his data that he gathered fit the pattern over a wide range of wavelengths. It didn't fit for just one part of the electromagnetic spectrum. It fit for the whole thing. 5 years later, Albert Einstein came into the picture. He was a German-American physicist, and he used Planck's stuff to solve the mystery of the photoelectric effect, which could not be explained by the wave nature of light. The photoelectric effect describes a phenomenon where electrons are ejected from the surface of certain metals when they are exposed to light of a minimum frequency, a threshold frequency. So you shine light on something, and it ejects electrons. And a lot of the times the electrons jump up and then they relax back down, and you get a light that you can detect. And like with our flame test lab, we could detect that with our eyes. Okay? And that's very similar to what is happening here. Okay, energy is passed through a tube filled with an element, and then the electrons move and they give off very specific color patterns. The fact that light is interacting with a particle, a wave interacts with a particle like it was a particle, was interesting. So the number of electrons they saw ejected was proportional to the intensity or the strength of the light, but the energies of ejected electrons were not. The energies were always the same, but how many electrons would increase if you increase the strength or intensity of the light, but decrease if you decrease the intensity of the light. So they always had the same energy, but how many came out was different. So Einstein saw this and proposed that the beam of light was really a stream of particles of light. We now call these photons, and we know that each photon has an energy equal to h times nu, or frequency. The idea that light was composed of particles explained the photoelectric effect. However, it was not consistent with the known wave behavior of light. So scientists scratched their heads a little bit, and they decided that light must have both particle and wave natures, depending on the experiment being performed. This work also paved the way to explain other phenomena, such as when light passes through a prism, the light that comes out appears as a rainbow. And if you do the same thing with a gas discharge tube, which we will do later in class, filled with hydrogen, basically a hydrogen light bulb, you don't get a rainbow. You only get 4 strips of light, not a continuum. This indicated to them that electrons have a fixed energy as well inside the atom, like energy levels, based off of these 4 colors. So each element has its own emission spectrum, so they can be used to identify the material present in a sample. This was done during class when we did the flame test. You guys ran a test on 11 different substances, gathered data, determined what determines or what indicates the color, what element or type of element indicates the color, and ran an unknown test and were able to identify that unknown based off of your data and the color of the flame, the unique color of the flame. So later, Niels Bohr presented a theory to explain the line spectra for different elements, like the hydrogen gas tube. In his theory of the atom, he had the solar system or planetary model where electrons travel around the nucleus in specific orbits. These specific orbits were dictated by quantized energies. When an electron absorbs energy, it can move from an energy level that is closer to the nucleus to one that is further from the nucleus. This was called an excited state. When the electron drops to a lower energy level, energy is released in the form of electromagnetic radiation. And since orbits around n = 6 atom, like that's close to the edge of the atom, are fixed, the energy differences are quantized. So then using E equals hc lambda, each energy corresponds to a specific wavelength. If the wavelength is between 400 and 700 nanometers, our eyes can detect the energy and it will appear as color of light. So we will see a colored light. So here is the emission spectra for a hydrogen atom, and it gives off very specific. It's missing one of the transitions, but it's okay. This specific transition is called a Balmer series. There are multiple series though. I'm not going to ask you to memorize these. So each atom can only undergo one transition at a time. So one atom can do one of these for hydrogen at a time. But in a sample size of a light bulb of hydrogen, there are many hydrogen atoms that are all gaining and releasing electromagnetic radiation. So some will be doing this one, some will be doing this one, and some will be doing this one. but not all three at the same time. And so you will then see, but because some are doing each one, you will see all 3 or 4 colors. Okay, this theory provides the foundation of the currently accepted quantum mechanical model of the atom. So now we're going to switch to the I do. Okay. We're going to calculate the wavelength, which if we look at our equation, wavelength was lambda, of a wave with an energy, E, of 1.83 times 10 to the negative 19 joules. Okay. So we need to find an equation that has both. So E, looking at our equations, hc over lambda, this one has both. However, we want to solve for lambda, so we need to rearrange. Lambda is being divided, so we want to have it on the top, so we multiply. It cancels out here. We still need lambda by itself, so it's being multiplied to E here. We want to move E to the other side. So we divide. So we get lambda is equal to hc over E. Coming up here, lambda equals hc over E. We can now substitute in for what we know. We know h, that's Planck's constant, it is always the same. C is the speed of light, and it also is always the same. And then E is given to us here. So substituting in 6.626 times 10 to the negative 34 joule seconds times the speed of light then divided by energy, and then we're ready to put this into our calculator. So solving it in our calculator, we enter in 6.626 E negative 34 times 3 E 8 divided by 1.83 E negative 19. And you should end up with 1.09 times 10 to the negative 6 meters. And that is our lambda. Okay, so what is the frequency, which is nu, of light with a wavelength, lambda, of 434 nanometers? So we need to identify the equation that has nu and lambda in it. We see that that is C equal to lambda times nu. We want to solve for nu, so we need to move lambda to the other side. So divide by lambda. And so we see that nu is equal to C over lambda. We know C is 3.00 times 10 to the 8th meters per second. And then lambda was given, which is 434, but we have to change nano to times 10 to the negative 9 so that we have meters and meters, so that the meters cancel. Now we would plug this into our calculator, and you should get 6.91 times 10 to the 14, and this is per seconds. Per seconds is the same as saying seconds to the negative 1 power, because it's in the denominator. Putting it in the numerator gives it a negative exponent. Or per seconds is also the unit, a new unit for us, hertz, Hz. Okay, so our frequency is 6.91 times 10 to the 14 hertz, or that many waves per second. Our final redo is asking what is the energy, so E, of light with a frequency, which is that curly V we call nu, of 1.97 times 10 to the 15 hertz. Remember that that is either per second or seconds to the negative 1, so it would cancel anything that is seconds. So we need to then find something that has energy and frequency in it, which would be the equation E equals h nu. We know nu and we know h, so we don't have to rearrange the equation. We can just substitute in. Planck's constant is 6.626 times 10 to the negative 34 joule seconds. And then the frequency was given to us as 1.97 times 10 to the 15th hertz. Hertz is per second or seconds to the negative first power. That cancels this second. Okay, and so we are left with energy of units of joules, which is for energy. Plugging this into our calculator, we end up with 1.31 times 10 to the negative 18 joules. And that is our energy for this wavelength with a frequency of 1.97 times 10 to the 15th power hertz. So now it's time for you to do the U-do. For number 1, you will use this spectra. So you might want to pause the video here and do number 1. For number 2, you want to flip back into your notes. To this graphic, so it's the very front page, to do number 2 in your notes. And then the rest should follow from your notes and the example problems. Thank you, everyone. And please, please, please do not forget to do the guiding question at the end of your notes. Thank you.